So hi, I'm here to talk about Apache Mynewt. It's a bit higher in the stack. This is an operating system that we put forward for constrained devices. It's in the Apache Software Foundation. It's designed to run on MCUs in the IoT space. What I'll do is I'll talk about, obviously I'll talk about this, but philosophically why we think it's a nice match for RISC-V and some of the design decisions and components here. So a little bit about my company. It's a company called Runtime. Our backgrounds, the founders of the company and the core embedded team, we came from a company called Silver Spring Networks. We built communications modules, the firmware that ran on these modules, and we put them into things like electric meters for industrial IoT. We deployed over 23 million of them and had to manage them. On the comms modules themselves, we designed our own system on chip. We drove two transceivers. One was a long reach network, sub-gigahertz, narrowband frequency hopping. We took that to the IEEE and standardized that. Really the design goal there for IoT was around driving long ranges at a trade-off for throughput. So point to point, we channelized at 300 kilohertz. We drove these narrow channels at a full watt, and then we meshed. So it was a big meshing network. We deployed into utilities like Pacific Gas and Electric, Florida Power and Light, et cetera, et cetera. So really there's a hugely different set of constraints on these types of devices, not the least of which is cost, and then you're confronted with management challenges here as well. We left that company. We surveyed the IoT space. We knew we didn't want to sell solely to utilities, and we knew we didn't really want to build hardware. We started looking at a lot of product companies out there. We looked at their tool chains and their ability to manage their devices, fleets of intermittently connected devices that are constrained, typically Bluetooth, and we found it pretty wanting. The original idea was to build a cloud service for management and monitoring, things like wristbands, locks, light bulbs, doorbells, for companies that are building product for consumers. And we found that they were essentially reinventing the wheel. We looked at client libraries and agents as a way to instrument their products and talk to a cloud service. And the heterogeneity that's out in the field is just too great. So we didn't intend to build an operating system, an open source operating system, but in order to get homogeneity, we did that, and we put it into the Apache Software Foundation. I'll talk about a lot of the elements there, but the idea behind the OS, well, we looked at a number of different RTOSs that were out there, and for product companies, many of them didn't want to be encumbered with paying ThreadX or Micrium or others that are out there. And then there's a number of GPL that don't have permissive licensing, which we considered. One of the goals of the project itself is hardware agnosticism. We looked at embed from ARM, and interestingly there, you're asked to write a check. They would like you to sign a contract and constrain the ports to Cortex-Ms. And then if you're building a commercially supported release around it, upstreaming your changes and having some determinism as to what actually goes in the builds, that was found wanting too. So we were really pleased when we heard about RISC-V. We think this open source operating system is a nice match for it philosophically, and we think there's a lot of components there. We'd really love to see the operating system serve as an abstraction level. What you need, what we found that product companies need is commonality or homogeneity across the bootloaders, across how they instrument the transceiver itself, how you instrument and monitor the tasks in a task table. The processor and the transceiver need to be abstracted as well. So, as I was mentioning, you talk to a lot of companies that are building these products. They get a small amount of runway, a small amount of money, and they decide that that they'd like to put an RTOS in their product, and then they're essentially left with cobbling together a lot of embedded middleware components or services. If you're a Linux guy and someone hands you an operating system, you expect to have file systems, you expect to have network protocol stacks, you expect to have source code available. And so what we found is a lot of times corners are cut early in the product. Everyone implements circular buffering schemes themselves, for instance, or has to modify bootloaders. If they don't do that, the initial product's going to be shaky, and they're going to incur technical debt. And really, you see a lot of nascent IoT products that are fragile. So that was a motivation. Another motivation or a result of us open sourcing this OS is that we see a trend also, and our first products, our first operating system or instance of it included the world's first open source Bluetooth low energy stack for microcontrollers, and that's down to the controller level. What we saw there in that industry is a trend of more and more powerful platforms, if you will, for MCU-oriented devices. So if you look, our first port was to the Nordic NRF52. It has 512K of flash, 64K of RAM, and we're seeing products from other vendors that are coming out with a lot more flash, a lot more RAM, and what you're seeing is this basically coalescing of a lot of different components into systems on chip, and these systems on chip can't run Linux, they can't run Android, they can't run Brillo, they don't have memory management units, and yet they deserve an operating system, and they deserve a rationalized tool chain that can be used across different hardware platforms as well. So you can imagine an implementation today running on a Cortex-M, and then when commercial products out there, easily transitioning that over to a RISC-V based implementation. And from a user perspective, a guy who's built a product and has to operate it in the field, all of the upstream interfaces, the bootloader and the instrumentation, the logging infrastructure across the transceiver, the processor, and the OS, those remain consistent. And that's something that, and that's one way to solve the heterogeneity problem, other than just giving them a chipset. So we see this convergence here as well, and we'd love to see similar types of chips based on RISC-V. So I think I alluded to this as well. The product developer typically, if they're not, when we first talked to one company, we asked what OS they were running, and their product manager said BLT, and we looked puzzled and asked what BLT was, and they said big loop technology. So there's a lot of while loops out there, but a lot of products are becoming more and more complex. One transceiver, multiple transceivers, a lot of sensors, and you're even seeing maker kit that's having a lot more complexity and actually needs real operating systems as well. So these guys, they pick the OS, and then they have to cobble together a hodgepodge of services or embedded middleware. And so included in Apache Mynewt is not just the kernel itself, but a flash file system, a lighter weight TLV-based storage mechanism on flash, circular buffering scheme, bootloader, secure bootloader, the Bluetooth stack that I mentioned that's open source down to the controller level, a logging infrastructure that's JSON-based to pull all of that data out and convey it via gateway to the cloud, and a build and package management tool that's based on the Go language, GPM, that looks sane as well. So we think from a perspective of nascent product builders, this is the plumbing on the embedded side that allows them to just make a no-brainer, free, permissively licensed choice embedded in their product, and then focus on the customer-facing aspects of the product as well, and without incurring technical debt. So end-to-end, I'm not going to dwell on this. End-to-end, this is the current stack with Apache Mynewt. The first networking protocol was Bluetooth Low Energy 4.2. My company Runtime has represented Apache Mynewt at the last 2 Bluetooth SIG Unplug Fests, and we expect to certify within the next 6 weeks. That's going really well. And Bluetooth has an interesting trajectory with Bluetooth 5, where there'll be more range, bigger packet sizes, better throughput, IPv6 and meshing. So I think the envelope of use cases will be extended as well. And that's the first network interface. We're also putting a socket interface to Wi-Fi for now. We've been announced, or Arduino has announced that this will be the OS for the Arduino Primo and the Arduino Otto, which have an nRF52 and an Espressif Wi-Fi chipset on it as well. Part of the distribution as well will be gateway code on iOS, Linux, and Android. And then the company, Runtime, has a proprietary cloud service. So a bit on the Apache Software Foundation initiative. We think it's a great place for this type of effort. It's community-driven, meritocratic. If you're a committer, you get a vote. You get a vote as an individual. It's not a company alignment there. If you leave your company, you still maintain your committer status, and that's based on merit, having been voted in by other committers. And what we're talking about is building an operating system for these microcontroller environments. And you've seen, or we're seeing a couple of initiatives that are out there. ARM has Mbed. I mentioned some of the attributes of Mbed, the Mbed program. Intel initiated something called the Zephyr project in the Linux Foundation. It's our view that operating systems, particularly if they're going to be hardware agnostic, having a balanced ecosystem and not being pushed forward by one chip vendor is probably a good thing for users in the community. So there's a lot of constituents here, including MCU vendors. These are just, there's nothing special about the particular labels there. It's just trying to illustrate kind of the balance that we think you need in order to drive an operating system. The users today, our users, the Apache Software Foundation, Mynewt project users, are really what's driving this is the open source Bluetooth stack. It's a pain point. It's currently at a 0.9 release, but the kind of the state of affairs, or the state of the world is today you buy a chip from a chip vendor. Typically they give you a licensed binary. It sits between you, the application developer, and the MCU. It steals interrupts, it smashes the stack. It makes debugging very hard. You don't have source code, and typically the configurations are fixed. So for instance, one implementation has 3 concurrent connections in central mode, 1 in peripheral mode. Some of them are throughput constrained, and having access to source code allows users to actually debug things and optimize their implementation if they're related to those parameters. And we do see Bluetooth growing. I mentioned Bluetooth 4.2 to 4.5. I think, as far as kind of coalescing around single SoCs that are cost optimized for a lot of products, I think there's going to be a lot of opportunity for kind of sub-gigahertz low power wide area networking. That seems to be an ideal place. Today, a lot of these long reach applications, typically people are slapping a module on top of another processor, and that's not ideal for cost. I think if we can drive cost out of these products, you'll see more controllers out there and more connectivity. The project has been going actually since October of last year. That was 280,000 lines of code. A lot of it's driver code, but that's grown since then. We really only started socializing this in March of 2016, coincident with Bluetooth World, when we did announce that open source stack. What you see is a number of platforms that are supported. I mentioned the Arduino and Primo and the Otto. We'd love to have RISC-V developers looking at this OS and considering it for as an OS that is philosophically aligned and technically suited for the MCU applications here. I mentioned a build-in package management tool. What we've seen often is, and one of the things I think that's interesting about this implementation is we've kind of coalesced 4 different elements here. One is the notion of an operating system as a whole. Often in the embedded world, people think just in terms of kernels and then piecemealing the different elements that they need together. We try to provide all of those components. So thinking expansively in terms of an operating system, I think, is useful. 2, I think having the composability there and having this built-in package management tool in order to, a modern built-in package management tool so that these things can be assembled pretty easily, and it can be a tool chain that's independent of particular vendors' MCUs, we think is useful. And then the abstraction that this OS provides and the composability, we're finding, the OS is suited for products that go out in the field, but we're finding the maker community is coming in, jumping on the project as well. We initially put Lua, an interpreted language, in the first distribution. We've had a volunteer come in and put MicroPython in, and someone's working on JavaScript right now. So you're getting really simple interpreted languages that make it accessible and kind of democratized. The OS itself abstracts away the hardware and the board support, which is pretty useful to the community as well. The project structure, this is imminent. Right now it's a monolithic project within the ASF, but we're breaking it out to different components, and there'll be different teams of committers across those components. This also corresponds with the philosophy around the built-in package management tool. Multiple repositories. You can pull from the Apache Software Foundation repository. You can pull from a GPL repository if you choose, or you can have opaque binaries from another repository. There's a lot of flexibility there. The BSP and the how, we've gone to great lengths, or are going to great lengths, to make this simple for novice or maker-style developers, but also provide the hooks to peripherals for guys who are more experienced, and to really do discrete power management and discrete control of all of the peripherals. The kernel, we looked at a number of OSs that were out there, or RTOSs or kernels. We developed our own. We wanted a preemptive kernel. A lot of, I think, academic approaches look at the OS or the kernel as an afterthought, and perhaps they'll put Kentucky or something small on it. We think if you really want to commercialize the actual implementation, top to bottom, having the right OS with the right kernel there is going to be useful. It's tickless, so the design for good, solid power management as well. Energy efficiency, I have 2 slides on this. I'll just talk to this one. Energy efficiency is I think, paramount. I mentioned that what we're seeing in the Bluetooth space is these monolithic license binaries that you get from vendors. Often, these aren't optimized for power, surprisingly, or they could be better optimized. If the application developer knows his application well and has direct access to the peripherals, which he doesn't in many cases today, we think that vast improvements can be made here as well. And security, the IoT space is I think it's hard to not look at the press and see doom and gloom around security of consumer IoT products and even industrial IoT products. We've tried to be thoughtful about modularly allowing or enabling security. The bootloader that I mentioned is a 2-stage bootloader. Basically, you can download signed images and verify them. It's our commercial intent to provide tools to manufacturers such that they can establish identity at time of manufacture and secure credentials, and this allows it allows essentially verification with the back-end cloud-based system as well to ensure network admission control under the cloud as well. There's a simulator here, and we try to make things simple within the project. All of the tool chains, the simulators there, it provides a pretty straightforward way to develop your code, but there's also, we Dockerize across Windows, Linux, and Mac OS X as well, so that the tool chain based on GCC, OpenOCD, and JLink debuggers are all available as well. And then the near-term roadmap to 1.0 GA, which is targeted in October, is here. I think notably the Wi-Fi and IP support is coming in the next month. The certification of Bluetooth is happening, and we really want to build in long-term API stability in the 1.0 timeframe. And then I think I alluded to it. I think one of the things that the project needs is an interface, and it lends itself to that concise SOC implementation is a low-power wide area network interface, which will be provided. Could be LoRa based. It might be IEEE 802.15 4G based as well, and that'll be coming. I think that work will be kicked off around GA. So really, in summary, I think we wanted to introduce Apache Mynewt. We think technically it's compatible with MCU-based RISC-V implementations. We think that philosophically the ASF shares a lot of the attributes of and kind of spirit, royalty-free, community-driven implementations for these low-cost devices. So any questions?
Awesome.
Yeah.
Any questions for James? Yep.
Hi, I'm Ben Barenblatt from Google. I was wondering if you could tell us anything about inter-process isolation in Mynewt. Is there anything that will leverage the features of like the MPU on an M3 or an M4 that can get better isolation between processes? Yeah, about the closest we've come yet. The project started in October. This has been nuts and bolts. So to that level of compartmentalization, no, we haven't taken advantage of that or some of the trust zone attributes that are available in Cortex-M line. I think what the community needs is some abstraction across that and cognizance of other MCU architectures, and then how we do that in a consistent way. The closest to process isolation I think that we have right now is the interpreted languages that I mentioned, but that's a far cry from I think the granularity that you're looking for. But it's an aim, and we can always use the help. Great, thank you.
Dave Patterson from Berkeley. I had a couple things. Like, what's the name come from?
It was a co-founder's daughter. She liked lizards.
Okay.
Mynewt is a homonym for.
Yeah, and I gotta say,
something very small.
I think as a old timer, I'm embarrassed how bad security is,
Yep.
and I'm excited about some new promises about things that hardware could do for security,
Yep.
like in SGX.
Yep.
Not having a memory management unit in Internet of Things, doesn't it seem like the press is correct in being worried if we're going backwards in hardware? So is there some reason to be hopeful? Do you see directions where security is going to play a bigger role?
Yeah, I mean, back to the previous question, I think we need to do more at the lower levels of the stack where interfacing with the hardware. We've looked at the trust zone stuff. We've also looked at some of the stuff that MIPS has done. I personally haven't dug into where RISC-V is in that equation, but trying to rationalize across, say, those three platforms I think would be useful. What we've done is kind of perfunctorily put together the security around the bootloader, And then I think we're leaving it, which isn't the best answer, but leaving it to the higher layers in the stack at the application layers to do some of the security as well. That said, our BLE implementation right now is really nascent. It's based on 4.2. It doesn't have an IP stack, and there could be some improvements both at the lower layers and the higher layers of BLE. But the other thing is, what is your kind of the contours of your RISC with a Bluetooth Low Energy implementation? It's about 10 feet, so well, maybe a little more. But as we get longer reach Bluetooth Low Energy and longer reach networks, we're going to have to secure the endpoints better. Did that answer your question?
Yeah, well, I think
Yeah.
also to some
So maybe just to comment on the governance framework and the technical committee and marketing committee and the task groups will form underneath them will very much be driven by interest of the membership and who wants to work on those various task groups. So that's what we'll be discussing tomorrow during the member meetings. And the priority of the task groups that we want to put in place.
Yeah, and I'd love to see companies that are members of RISC-V who are really on the cusp of getting implementations that are going to hit the market. It would be great to see that driven sooner than later.
Hello, Jeroen Domburg from Espressive Systems here. I have a question with regards to multiprocessing. With RISC-V supporting multiple hardware threads and in general multiprocessor chips making some inroads in the embedded market, also the very small embedded market. Does Mynewt support SMP? And if not, what would be the schedule?
Yeah. No, it doesn't. It's going to be the same answer as I delivered to the gentleman from Google. Early days, single microcontrollers, cost-constrained, constrained devices. We'd love to explore that. We've got some customers and a number of people have inquired about, at least in the ARM world, coupling Cortex A9s with Cortex M4s or M0s. And right now, we're really suited for the M0 and M4 class and solely for those. But it's an aspirational thing.
Andreas Koch, TU Darmstadt. Could you compare and contrast Mynewt with Contiki?
Yeah, I could probably do a better job, but at least on the surface, one, we wanted a preemptive kernel itself. Two, we wanted the notion of an expansive OS that included a number of different components. And I think Contiki does a lot of those, but it was really kind of pulling in the file system work, the TLV storage mechanisms, the circular buffering schemes, all the bootloader, and the bootloader tools with the hooks for over-the-air upgrade, and then logging infrastructure across that with instrumentation across the processor, the transceiver, and the task table. Kind of all that put together with a built-in package management tool. That was the idea. We could have used Contiki. We elected not to do so. I think I'm probably not the best to go into all the technical reasons. We did look at Riot as well. Had it not been GPL'd, we probably would have gone with that kernel. There's been a lot of really good work in that project as well.
Great. Thanks, James.
Yep.
That was very cool.
Yeah, thanks.